morning, everyone. All good things come to an end. Yeah, and today is the last day of our summer school. I think it was a busy February for all of us. Thank you very much for staying with us till the bitter end. Yeah. And this now is the last lecture of the course of Christine Kraamwinkel on statistic using R. So I don't need to introduce Christine anymore because you know her very well. And yeah, Christine, please, you already started your poll. I think we need a few more takers. So Christina,
yes.
You're welcome to start. Thank you very much.
Thank you so much, Prof. Yeah, so welcome everyone to the last class. So today, like the heading says there, we are going to look at some linear regression models. And then we will also just go back. So we'll start with just a quick promise that I made you guys on Tuesday, that I would go back to show you what happens if your data set violates the assumptions needed for a chi-square test. So we'll start with that. So we still have 7 seconds left in our poll. Let's see if anyone else wants to share how many pets they have. So far, it's even between 2 and 5. And I think it stays that way. Almost looks like someone has 25 pets. Now that would be a lot. So let's get back to the lecture, and then we're going to keep it quite simple. I first want to just check, does anyone have any questions about hypothesis tests? Anything that anyone's unsure about? As always, feel free to just switch your mic on or type in the chat. Doesn't look like anyone is unsure about anything. That's fantastic. So we'll do some no, there won't be a hypothesis test today, but yeah, actually there is a hypothesis test in today's class as well. Sorry, frog in the throat. So okay, so before we carry on with the linear regression, I'm actually just going to switch over to R quickly, show you the chi-square bit that I promised. So when we did this chi-square test yesterday, we saw that there were no issues with our assumptions. All the assumptions were met. Our expected counts were more than 5 in each of the categories. But I wanted to show you that R actually does also look out for these things. So I found the data set, the ASOF data set. So if we look at that data set, what it has is data on smoking, alcohol, on those two things, on esophageal cancer. So in the data, we have a bunch of age groups. You have whether or how much alcohol the person consumes per day, how much tobacco they consume a day, number of cases, number of controls, things like that. And then you can also see here where this data came from. So it's data from the 80s, and see some extra code associated with this. So in this data set, just to get an idea of what the data looks like, if we look just at the first 6 rows of data, you can see there we have our age groups, and they actually didn't give us the coded data. So in the information here, they show us the coding that they would have used, but actually they're not displaying the coding. They're going straight into the numbers here. So I decided, let's go do a table of age group against the alcohol consumption. And you can see these are in categories. We're not really dealing with these. Even though it's numerical data, it's given in categories, so we can see it as categorical data in this context. So if I run this code to view the counts, we can see that we have 4 people in this category. We have 4 people there. We have 3 people there. Now, that in itself is not the issue. The issue is our observed values our observed counts don't need to be 5 or greater, but our expected counts need to be. And if we look at this table, we can actually very clearly see right from the start that in all of these categories, we're going to also end up with expected counts less than 5. So it's not always the case. Let's say all of these values were much larger than 5. One of these cells was less than 5. Then maybe we wouldn't have even had an issue. But yeah, we can see that we don't have enough data really to get expected counts larger than 5. So we would have to combine categories if we really wanted to do this. Now, if I run this test, I've just called it test 4 here, and it immediately gives me a warning. So it does run the test, but then it tells me, listen, this approximation may be incorrect. So just take note of it. Don't go say that this is now the be all and end all of everything. So what I also wanted to show you here is that we can now also display those expected counts. So like I said, you have access to quite a lot of information here. You can see all the observed counts, you can see the expected counts, you can see your residuals, standard errors, or standardized. I think that is probably standardized residuals, not standardized error, or standard error. So if I go and just display the expected count here, you can see that all of these expected counts actually are less than 5. So this data set isn't really appropriate in the format that it is for the specific variable. We actually shouldn't be doing this chi-square test on it. So R does warn you. So if you've forgotten that, you do get warnings, and it's not this different for other tests either. So often if R knows that there's an assumption that needs to be met and it isn't met, it will often give you a warning. I won't say every single time, but often you will get a warning about that. Any questions about this before we move on to the linear modeled or linear regression? It doesn't look like it. So we'll get to the code just now. Thanks, Martin. So first we'll just look at a little bit of theory. So again, not too much theory. So basic linear regression model, I think everyone knows this. So I just put everything on here just for completeness sake, and so that we know what beta 0 and beta 1 is. So beta 0 is just my intercept parameter, which gives us the mean value of y, whatever my response variable is, if x is equal to 0. So if my predictor is 0. Now, it's not always possible to interpret this, and we'll see that with our example today. We can decide whether it actually makes sense to interpret it. So sometimes it will make sense to interpret this parameter, sometimes it won't. Now, our slope parameter, we're going to call beta 1, and that tells us whether there's a relationship between x and y. Now, if we then look at our what we're actually going to apply, I've just changed it over from beta to b's. Then we know this is our estimates of these parameters in the linear model. One other thing I didn't mention here is we also have an error term. So this is not a deterministic model. If it was a deterministic model, it would mean that if I have x, I will always know exactly what y is. So we know that's not the case. There will be some randomness. So there's some random error term that's also included in this model. But we can't model that error term. So that error term is always going to be a random component that we, for some reason, can't predict. So it might be that another variable has an influence that we haven't accounted for in our regression. Yeah, we just can't explain it. We just accept that there is it's not going to be a perfect prediction. There's going to be some error that we can't predict. Now, we are luckily not going to do what people do in school and in first year and have to do these calculations by hand. That's why we have R. It will do all of these estimates for us. And it's very straightforward. So there's just a few things that we need to keep in mind when we do these models. So firstly, the pairs of points. So the each XY pair needs to be independent of any other XY pair of points. So it doesn't mean X and Y are independent of each other, because if they are, then there's no point in fitting the linear regression line really. So it's the pairs of points are independent from the other pairs of points. So I hope that makes sense. Then the other thing that's very important is that our error terms need to be normally distributed, centered around 0, so mean of 0, and have some constant variance. So we don't know what that variance is. We've just called it sigma squared here. We can estimate that variance, and R actually does that automatically for you. But we don't need to we don't need to know what that is. We just need to make sure that we have constant variance. So that just means that if we're plotting our residuals, and we'll look at an example of that later on, it needs to be constant, that variance of the error terms. So the error terms are also, they should be independent of each other. There should not be some, let's say for instance, a time, like based on times of observations, that those are like correlated with each other. They need to be completely independent of each other. And that would then mean that our response variable would end up being independent of each other as well. So that's just a basic overview of linear regression. Now, if we look at model accuracy, I think you can all guess what data set we'll be using today. We're going to look at a few different things. So the model utility test, all I'm going to tell you about this test is that we're looking at the intercept parameter, and we want to make, not the intercept parameter, the slope parameter. So if we go back to that model, it's this parameter here. We want to go and check using the model utility test that that is a significant parameter. So basically what we're saying is if it's beta 1 is equal to 0, then it is not a significant parameter. If it is not equal to 0, then it's a significant parameter. Because if you think about this equation, if beta 1 is 0, then it basically means that y doesn't have a relationship with x. So that is what we're going to look at. Now, there's two tests that we can actually do to go and check this. So you can do a test with the t distribution, or you can do a test with the f distribution, and there's a link between the two. If we square t, we end up with f. So you'll see in the output that we're going to get that we'll get both for t and for f. We'll get the p-values and everything. Both of those will give us the exact same result. So if you actually go compare them, you'll see we end up with the same results there. Now, and that the p-values actually end up being exactly the same as well, which makes sense. So then other ways of also checking model accuracy or adequacy is to go plot or do quite a few different plots. So we want to go plot predicted values on the horizontal axis against observed responses on the vertical axis, and you compare that to a 45-degree line. So that's actually the line x equal to y. Which makes sense intuitively. You want to see if how close the predicted values and the observed values are to each other. And the closer they are to that 45-degree line, the better the predictions were. So the less of an issue, the less error there was in our predictions. Then the next thing we want to do is we want to go and plot our explanatory variable against the residuals. And we want to go and check whether the residuals are random, whether they're constant or that variance is constant, and whether they're centered around 0. Same thing with the predicted values against the residuals. We're checking for the exact same thing there. And then the last thing is, like I mentioned on the previous slide, normal, our residuals need to be normally distributed. So we want to go and check that as well. If they're not normally distributed, then maybe a linear model isn't the right way to go. So we're going to do all of that with the Possum data. So then checklist for the residuals, just to make sure we're all on the same page. We want to check, are the residuals normal? Are they random? Are they scattered around 0? Do they have constant variance? And that is pretty much what we'll be doing today. So first thing we do, before we even do a or fit a linear model is we would want to go and just do a scatter plot of our data and see whether a linear model makes sense. So if I do a scatter plot and I see the data looks kind of like the shape of a parabola or a polygon or something like that, definitely we're not going to waste our time fitting the model. So we want to at least see some form of a straight line in there. And then we can see how well the model fits. So what I decided to do is we're going to go back to the possum data because we're used to the data and it seems to make sense to use that. So we're going to use the skull width and head length variables. And the model I want to fit is I want to predict a possum's head length given their skull width. So skull width is going to be my independent variable and head length is my dependent variable. So for this, I'm going to actually use that trick that someone taught me the other day. And we're just going to say attach and possum so that we don't have to type the whole thing every single time. So now we can do a scatter plot of the possum skull widths and head lengths. So I'm not going to worry about labels and titles and things because this is just a preliminary check for us. So if we're going to publish this, then yes, please put the titles and the labels and make sure it's very clear. For this, we're not going to worry about that too much. So we know in this plot function, if we do a scatter plot, we did that in one of the previous classes. If we do a scatter plot, the first argument is our X value. So that is going to be our skull widths. So we that on the x-axis, and then the head lengths will be on the horizontal, the vertical axis. And there we have it. So now I want to know from you guys, what do you think? Would we dare do a linear model in this case? Is there anything that's bugging you? So feel free to put in the chat or switch your mic on, give me your opinions. Yes. Okay, so Isaac, if you look at this plot, do you think just by looking at this plot that a linear model is appropriate? So Benjamin says maybe rather a polynomial because of that curve, I'm guessing. So yeah, so if we didn't have those points, so let's pretend those 2 points aren't there. Like maybe we can get away with that straight line. So yeah, those 2 points, if we ignore them, then it changes the picture a little bit. So I personally, I look at this and I think maybe we can do it. Maybe it's just those 2 points. Those are going to be the interesting things to look at. But let's fit the model and see how it turns out. Okay. So we can calculate correlation as well. And we can guess the function yet again. So you can see there's a car function and then it pops up here and it says this, the variance, the VAR, COV and COR compute the variance of X and the covariance or correlation of X and Y. So we know this is the right function. So we're going to do correlation of skull width against head length. And if I run that, I get a correlation. So we can see here, it's not the strongest correlation, but we know in real life, if you get a correlation of 0.98 or something like that, that is very rare. So theoretically, this is moderately strong, I would say. There does appear to be a linear relationship. So correlation, just very important to note, it doesn't tell us just about any type of relationship. It tells us about a linear relationship, the strength of a linear relationship specifically. So in this case, it's not a perfect one. If it was perfect, it would have been 1. So correlation, when we calculate it, was always between -1 and 1. -1 indicates a perfect negative relationship. So if I had to go and plot that, it would have a downward slope, and it would, all the points would lie on a straight line. If it's 1, it would, there would be a positive slope, and all the points again would lie on a perfectly straight line. And we can see here there's variation, so we don't expect it to be exactly equal to 1. But 7, I don't think is too bad. So I think we can carry on with this. So now we can carry on with the model. Now, first thing, linear models. We are going to fit that using the ALIM function. Again, we can just guess it. So it gives you a whole bunch of information here. Again, you can see what arguments you have that you can specify. Most of these I haven't really used in the past, but yeah, you can go and see which are relevant to you. There's some more details here. Then it tells you what components will be found in there. So you'll see that in your output, you're going to have the coefficients of the model. You'll have your residuals, you'll have your fitted value. Then something about rank. And then weights, if you want to use weights for fitting. So if you wanted to do a weighted linear model, the residual degrees of freedom, there's a whole bunch of different things that you can find in here. It even stores the X and Y values that you originally fed into the model. And it can give you all of this information in your output. So then also time series data, if you wanted to use them in that context, there's some advice there. Some information about the authors. So these authors wrote this a while back, but I've actually found with some of the newer software packages, it's useful seeing who the authors are. I've run into some issues with some of my coding, or where we found a problem in one of the packages that we were using, and we emailed the author and said, listen, just want to check about this, and people respond quite nicely. So, so we got some good information that way. Then there's some references again, and in this case again, there's some examples here at the end. So you'll notice here, and this is a very important thing, you can actually do an ANOVA based on this model that you fitted, and there's a summary as well. And here it just shows you the how you could fit the model. So this is fitting weight as a function of group, for instance. So I just want to see here, to characterize outliers using the correlation function. I'm not sure about that. That's a good question. I'm just going to screenshot it so that I don't forget the question. And then I think I'll send you a message afterwards. I'll think about that. I'm not sure. If I give you an answer now, I'm going to be lying. So to characterize outliers using correlation function. So there's definitely, I think there would be other ways of doing it. I remember we did, when I was busy with my master's, we did a lot of outlier work. I haven't really worked too much with outliers in the data that I've been working on, but I'm going to find out, and then I'll get back to you about that. So yeah, so then for the linear model, I'm going to just call it ALIM model. So I just already wrote that there so that I don't forget what I wanted to call it. So for that, we're going to use the ALIM function. And then we want to predict head length as a function of skull width. And we can just go back up to this again. And just see, you can see here, that is the formula that we've entered here. So you can specify what data set to use. Let's see if this works without specifying that. It worked. Okay, so we ended up with a list here of 12 items. So if we view that, just quickly, you can see here that we have the coefficients, the residuals, the effects, the rank, the fitted values, all of those things that promise to us so nicely. We have all of that. So I can go and print this model just like that. So we could just say here ALIM model, or I could use that trick that I showed you last time. I'll just show that again. If I had just put all of this line in brackets and I run this, then it automatically outputs. So it runs the code, it assigns the value into that object, and then it also outputs. So whenever you do round brackets around an entire line, whatever's in that line will automatically be output as well. So there we have our coefficient, or both coefficients. So we have our intercept estimate, and we have our estimate that the slope parameter that we've estimated, or the estimate of the slope parameter, not the actual slope parameter. So we have that information. So it's not very much that gets output just like this. Now, we might want to now go do our model utility test, because if you look at this, our slope parameter is 0.8 something. Now, we might think, okay, but that 0 point something, is that really significant? So for that, we would want to do the model utility test. So I'm going to do summary, use my summary function of that ALIM model. And if I run that, I get a little bit more information. So this is now where it goes and extracts everything from here, and it puts it into like something that's a little bit more understandable if you understand what's going on here. So we can see here our residuals, what the minimum is, what the maximum is. You can see there that's almost -9. That only goes up to 6.5. Median here is 0.05. So ideally we would want this to be 0. We want, if the residuals are normally distributed, then remember the mean, the median, the mode all need to be the same thing, and we want the mean to be equal to 0. So we can actually go and check what the mean is. It hasn't shown it here. So we can use the mean function and just say, let's go access this linear model of ours and specifically go look at the residuals. So I can do that, and you can see this is a very small number, very close to 0. So you could also go say, let's just do a summary of this linear model, specifically the residuals. And if I run that, I actually get a more complete summary than the one that I've been given by this first function. And you can see here the mean is actually 0. Which makes sense. If you go into the math, then it actually makes sense. But that median, that is bugging me a little bit. But we'll look at all the diagnostics and then decide whether that's something to worry about or not. So the intercept term, we're not going to worry too much about that. But let's actually go back to this. So I said in like when we were going through the theory, I said that you can't always interpret your intercept term. So if you set your independent variable equal to 0, you end up with that intercept term. So that's basically saying if my independent variable takes on a value of 0, what is the average value that this dependent variable will take on? So in this context, if we try to interpret this, we would basically say, well, if my skull width is 0, then I expect on average the head length of the possums will be 46 centimeters. Does that make any sense? If my skull width is 0 centimeters, then I expect on average the head length will be 46 centimeters. Makes no sense at all. So this is a perfect example of a case where if you just went rogue, like you had learned this like a parrot, like how to interpret the intercept, and you're not applying common sense logic, then you are making a assumption here, doing an interpretation which actually makes no practical sense. So here, I would not interpret this intercept term because it's nonsense. So just be very careful of that. So we're not going to worry too much about testing whether that intercept term is significant. You can see the test does tell us statistically it's significant. We're not going to worry too much about the intercept term. Now the skull width, that is where that model utility test comes into play. So you can see here, we are actually doing a t-test in this output. We have our estimate here. We're getting them to a few more decimals than, well, one more decimal than we got in the original output. And if we look at this p-value, we can see that, yes, that is a significant parameter. So if you look here, they're even nice enough to tell you, like, give you a star rating for your significance. So you can see we got a 3-star rating here. This is very highly significant. So that is basically the thing that we're interested in here. Now, this test could also have been done using an F-test statistic. And you can see here, if you take this t-value and you square it, it's going to give you that F-test statistic. So those two tests are very much linked. And you can see we're ending up with the same p-value here as well, because it's the same test, just done using 2 different approaches and 2 different distributions. So at this point, we're happy. We know so far, if we're looking at this, yes, our estimate here, it's significant. We're happy with that. There appears to be a relationship. We can find our R-squared. So R-squared I haven't spoken about, but R-squared basically tells us that's our coefficient of determination. I'm sure you all remember it from somewhere in your career so far. But that also tells us how well this model fits in short. So in simple terms, it just tells us if this is a good fit or not. So again, the closer it is to 1, the better the fit is. Now, in this case, it's 0.5. So R-squared is actually a value that goes from 0 to 1. So we can see here, this is not the best fit. So maybe that's also something to be aware of. Now, what we also get in this output is just our residual standard error, which is useful if you want to do standardized plots, or you want to calculate standardized residuals. Then you do have that value here that you can also extract, and you can go standardize all of your residuals. It tells you how many degrees of freedom as well. Any questions so far?
Hi, Christine.
Hi, Floyd.
I have a question. It's kind of like this. So what happens when like sort of like here, when you have data that when you are doing your own sort of like observations before running let's say maybe this linear model and all of that, what happens that you are seeing sort of like some significant based on what you can see that there is actually a difference, or you were observing, let's say you were running an experiment and then you were observing certain parameters, and then you see that there was actually a difference in the response of maybe, let's say, a plant. But then when you run the model says that there is no significance.
Then maybe you are looking at the wrong variable. So it could be that either it's the wrong variable to use in the model. It could be maybe that some of your other assumptions aren't met. It could also be that maybe you need an additional variable. So you might go into multiple regression and need more variables to explain what's happening there. One on its own might not give you the explanation that you need. Does that make sense?
Okay. So another question. This one is based on the correlation, because there's this other test that I kind of like did, and I had to do correlation between the two variables, but then there was sort of like one of the variables is that when you plot the variable, the issue is that when you plot, let's say you have a lower value and a higher value, they sort of like mean the opposite. So the lower value means that there is a lot of activity, and the higher value means that there is actually little activity. But then with the other variable that I was using, when you have a low and high, they mean what they mean. So if it's low, then there's low activity, and if it's high, there's high activity. So it became kind of like a challenge in trying to get a correlation, because I needed to get a correlation because there is sort of like a relationship between the two variables. And I didn't really know what to do, because whatever that you plot there is what they give you, and you can't sort of like change them in a sense to say that you're going to switch the values. So it became a challenge, and it's still kind of a challenge to now, because I don't know how to sort of like, you know, do an interpretation of that, because I need to do the correlation to see if the other variable corresponds with the other one, because they have a relationship somewhere, somehow.
Yes. So I think I would have to actually see this, but I'm thinking, so from what you explained now, if let's say both of those have high activity, then the one would be a large value and the other one would be a small value, right?
Yes.
Yeah, so then basically, and if there's low activity, it would just be the opposite way around, which kind of implies that you're going to end up with a negative slope, maybe, in the end. So I think you would have to think carefully about that, but I think I'm not an expert on linear models. It's not something I work with every day. We teach it, but we don't, like in my research, I haven't actually used it at all. So it's been a while, but I do have some colleagues that actually work on linear models, so I could check in with them. I think if you send me an email, then I can check in with my colleagues and see what advice I can get you, and see if we can help you along that way.
Okay, no problem.
Okay,
I'll drop you the email. Thank you.
Perfect. I haven't given my email address yet, but I will give it at the end of the session.
Okay, no problem.
Yeah, perfect. So then I see, is there any danger when one depends on one statistic or metric? Yes, there is. There is always a danger if we look at one thing in isolation. So for instance, if we think about hypothesis testing, there are so many different hypothesis tests to go check if your data is normally distributed. Now, there's some of them that work really well, some of them that don't. And like, as an example, I was setting a practical for my students last semester, and they actually don't do normality tests, but I wanted to show them that even though the data doesn't maybe look like, if you look at it, just trying to judge by looking without doing any tests, it's difficult to tell whether the data is normally distributed or not. So I showed them all the different hypothesis tests that you can do in R to check for normality. And we got conflicting results there as well. So some of them said, yes, this is normal. Some said, no, this is not normal. So we kind of went with the majority rules kind of approach. So it's good to know for each metric or each statistic or for each test that you do, what the strengths and weaknesses are, to make sure that those assumptions that the test or the statistic needs is satisfied, because otherwise you might pick one because you're comfortable with it, but not realize that this is actually in this specific situation not the best one to use. So that's, I think, the thing that makes statistics a bit more tricky is it takes a lot of experience to learn what you can trust, when you can trust it, and you do need to use some judgment as well. And that judgment you develop by doing more and more of it and learning these pitfalls. So I hope that answers your question. Any other questions?
Hello, Christine.
Hi, Isaac.
Yeah, good morning. Yeah, I have a simple question. I know when you are in developing a model, we mostly look at the p-value. So when you say when the p-value is greater than 0.5, you have to drop that. I mean, you have to drop that variable in the model. So I want to find out what about the intercept? Will you have to also consider the p-value for that one? So if the
Yeah, so in this case, I'm not too worried. There may be cases where you actually have to think whether that is an important thing to include. But like I said, I'm not the expert in linear models. I've done them, I've studied them, I've taught the basics, but I haven't actually applied it to my own data. So I don't have that experience. But yeah, I'm sure if you, I know a lot of the universities also have consultancy services. So I know at UP, we have a consultancy service that PhD students can, if they're stuck on their statistics, preferably before you collect your data, you can apply for help from the department. And then the people who specialize in the department in that can actually give you advice. They can point you in the right direction. They can help you with your analysis as well. I'm not sure if all the universities do that, but I know UP definitely does. We also have an external service that people can apply for help, but then of course it does cost money if you're external as well. So I would suggest maybe chatting with someone who works more in the linear models for an answer on that one. Cool. So then one other thing that you actually can do as well is you can go do this whole test to check for the significance of this parameter using ANOVA. So this is another thing that I wanted to just show you. You can use the AOV function. That is the one that we use for analysis of variance. So if you run that, you end up getting this output. So it gives you your sum of squares, it gives you your degrees of freedom, and you can see the residual standard error that die krag nou net afgegaan. Oh, sorry. Sorry, I thought we had a power failure. I just realized it's my dog that is unplugging my screen here under the table. Sorry about that.
No problem, things happen.
Yeah, no, we've had so many power failures this week that for a moment I thought when my screen went off, I thought, okay, power's off, now I need to go to the generator.
Probably so, your dog saw your pet Paul at the beginning.
Yes, well, one of them saw it. So no, she's always lying under the desk for some reason. She loves it there. So, and she's constantly unplugging things there as well. Okay, but then we are fine. We can carry on. So for the ANOVA, what I was busy saying is that there's our residual standard error. And you can see it's the same values that we had up there in that summary output. Same degrees of freedom is given here as well. So you're extracting a little bit of extra information here. So we can also go and assign this. So this ALIM summary, I'm just going to call it ALIM sum. We are running that, and we can again go see what terms we can extract. So if you look at the original model, coefficients, residuals, all of those things are there, but we don't actually see where it's storing the standard error. And when I was preparing for this, I had a look and I saw that if we do store the model, or not the model, let's just do that. I think my screen, my laptop screen, I apologize, is not the best. I think there's a loose cable. There we go. So here you can see that there is a, in here somewhere, there is a standard error. So I did find it yesterday. Let's actually just make this big. I'm just going to try, I think it's Control-Shift-3. No, Control-Shift-4. There we go. So if I go back into the environment, we should be able to spot it. So there's the call. You can see what terms we have in here. There's the residuals, the coefficient. There it is. So sigma. that's what they call it here. So if we go back to our console and we say ALIM underscore sum, and we go to sigma, then that gives us our standard error 2 more decimals than we got in that original output. So again, anything can be assigned to an object. Then often you can extract more information from it than you could before. So that is basically it for this. Now, if we look at this, we might say, okay, this is not the best model, but maybe it's acceptable. But like I said, we want to actually go and check those plots as well. Now, I've done a few of these. I've included the code already so that I don't have to type everything out now, and that you have it in front of you as well. So first thing we can do is plot the predicted values, or so the fitted values. They call it predicted values typically, but in R they call it fitted values. Doesn't matter what term we use, against our observed dependent variable. So if we do that, like we said before, we want this to fit on a 45-degree line. So we have that line there, and now I want to know what you guys think of the fit. Do you think this is close to that 45-degree line, or does it worry you a little bit? So remember what I said before? Yeah, it's a little bit, but yeah, it's also not 100% close. So remember, if our model predicted these head lengths well, then our observed values and our predicted values should be very close together, which would mean it should almost lie on this straight line. And we can see those 2 points that we had there, they definitely weren't predicted well with this line, which is not surprising at all. But there's quite a few that's a bit of a distance away from this line. So that to me is a little bit worrying. So that's the first one. So now I also, when I plotted this, I didn't speak about this code. We know how the scatter plot code works, but I've just shown you a new function as well, the AB line function, and that AB line function adds a line onto a plot. So if we do question mark AB line and I run that, then you can see there's a few different arguments. So you can leave A and B null. So A and B is your slope and intercept. If you want to do a vertical line, then there's a V function there. So that's the X value for vertical lines. There's an H value for horizontal lines. So you can choose what type of line you want to add. You can actually add multiple lines. So if I wanted to also go add another line here, I did a plot the other day of our pass rates for the module that I was teaching, where we looked at semester mark against exam mark, and then I added horizontal lines and vertical lines to show where the pass rate percentage was, and then also cutoff points, different cutoff points for the semester marks, and we can actually box the students up that way and see if there were any really good students that failed, or if like what happened with the marks. That's actually quite a useful thing that we show the students sometimes, to say, this is, if you are over here with your semester mark, expect to be over here for your exam mark as well. So you can do multiple lines if you want. In this case, we only need the one line. Now, explanatory variable against the residuals. So like I said, we can access our residuals. So if we wanted to view the residuals, we can just say ALIM model and access those residuals. And there we have all of them. So you can see they're numbered, and you can see they vary. There's negative ones, there's positive ones. if for some reason you wanted to look at the actual ones, this is it. You can also standardize from this point if you wanted to. I don't think these are standardized ones. Now, if we wanted to, we could also have printed out our predicted values. So ALIM model, and let's just do that, fitted values. So you can also print those out. And these, of course, correspond, it's just an index. So it corresponds to the first value, the first X value that you input. This corresponds to the second X value that you input, and so on. Now, if we do the second plot, so this was the explanatory variable against the residuals. If I run that, and I also add a horizontal line, we can see here where that reference line is. And remember what we said is we want these to be scattered randomly around 0. We want constant variance. So let's start with the variance. Does the variance look roughly constant, or are you seeing a pattern in the variance that it like increases or it decreases as we carry on? Is there a pattern, or? Any comments or thoughts? Should I pick someone at random? Who has not spoken yet? Okay, so Martin says no pattern. Saved by Martin, whoever was going to get called. So Martin says no pattern. Do you guys agree? I'm not seeing like a trend happening. I'm not seeing like an increase or a decrease, so it's not like funneling out or in. So maybe we can say, okay, this seems constant, there's no pattern. There's a little bit here that I'm worried about. Again, those 2 points seem to be a bit of an issue. But yeah, do you guys agree that it's actually hard looking at these things and then deciding? Yeah, it's, Shane says there's a bit of an oscillation. Could be, but it's very hard to judge this by just looking at it. So I don't blame you if you're unsure, because if I look at this, I'm also thinking could go either way at this point. Not the easiest thing to try and find it. So luckily there will be help, and we'll look at that just now. So we can also look here at the predicted values against the residuals. So if I plot that, there's the plot of the residuals against fitted values. And again, I'm adding a horizontal line, and it looks very similar. Not much of a pattern. There's maybe, if we look at this, it looks like there's a bit of an increase and then slight decrease again. So that, but if we take these out, yeah, then maybe we can say, well, it seems to increase as we carry on. So it's still difficult to see that. So we'll look at maybe we're still on the fence. I think we can say we're still on the fence about this. And we had our doubts from the beginning, so we can keep that in mind as well. So now we might want to go and check and say, well, the residuals, do they actually follow a normal distribution? So for that, there is a function, QQ norm, which is just a QQ plot. So again, so that's a normal probability plot, and you get other types of probability plots as well. I'm sure you've seen them before. So I'm just going to call up the help file for this. So Quantile plots, and they tell you a little bit more about this here. There's their usage. And And you can see that you can actually go check. You can do one sample or you can do 2 samples. In our case, we're going to do 1 sample. And then labels as before, as we did in the first sessions, you can go define them if you want to output this and actually use it as part of an article, whatever. You can go specify other things as well. So this QQ plot, all I'm going to do is just say, well, let's look at the residuals. So I'm going to use ALIM model, and I'm going to just access my residuals, access the wrong thing, residuals. And if we run that, we get that plot. So for anyone who can't remember how QQ plots work, it's basically if these values lie on a straight line, then it fits the distribution. So what we have here is our theoretical quantiles, comparing that to what we were observing. And we're seeing if they match, then that should lie on a straight line. But it's kind of hard to judge. If we look at this just like this, it's kind of hard to see where, if it's 100% straight, never easy to judge just like that. So what we can do is we can use the QQ line function to actually add that straight line for us based on the data. So I'm again going to say LM model, and again, just specify that I'm working with the residuals. If I run that, then there we have it. So what do you guys think? Does it look like my residuals are normally distributed, and why? If you had to put your life on the line here, would you say this is normally distributed or not? Yes. Tajuddin, I'm not sure if I'm pronouncing your name correctly. You're welcome to switch your mic on. See, you have your hand raised. I think you've clicked on your video button, not the mic button.
Christine, I tried to unmute him on my side as well, but it doesn't seem to work.
It's not working. There's the mic now.
Okay, excellent.
If you look at majority of the samples, we seem to that except at the extreme end and at the extreme end at the beginning, except those ends. But majority of them, so at least we can say about 95% of them fit normally.
Okay, so your sound is breaking up a lot. Maybe try switching the camera off, then we might hear you better. But what I did hear was you said about 95% of them seem to be on the line. Let's see if we can hear you better now.
Yes, at least 95% they are on the line. If you look at the middle, that is the major one we normally use if you want to use the QQ plots. So the extreme end, they may fall out of line or within that line, but majority of them, they are on that line. So we say they are normally distributed.
Okay. So you're saying yes, normally distributed because of the middle bit. So Isaac is saying the same. Martin is saying no. So we're a bit divided. So I would personally be very careful with this one because it's normally in the tail ends from so I'm hearing myself. Okay, now I'm quite. I think, can you maybe mute yourself again? There we go. perfect. Yeah, so it's a bit weird hearing myself as well. So from my experience, I've seen often that you would have data maybe that is like it seems fine in the middle, but the tail ends are the issue. And remember, if you think about the t distribution, for instance, it looks kind of like the normal distribution, but the difference comes in a lot more on the tail ends, that you have heavier tails. So this could maybe be an indication that something is happening here on the left-hand side of this distribution. So I'm a bit worried about that. If it was 1 point, then, or 2 points, then maybe I wouldn't be too worried about that. But personally, I'm a bit worried about it because there seems to be a trend happening here. It's not just 1 point, and all of these points are below this line. So it's not like they're bouncing around up and down. It just, something feels a little bit off. So we can, of course, go do some tests for normality on this if we wanted to. So could be more thorough. And there's, like I mentioned before, there's a lot of different tests that you can go and do. So most of them are, and I'm going to leave this as homework for you to just go and have a look at it. I believe there's a package called, let's just write here, package called NITheP, which I believe contains a lot of these normality tests. I think that's the package name. We can just check. I should have it installed. So let's just say library NITheP is the correct one. So you could go and do a hypothesis test. So let's actually just write that here. So NITheP for normality tests. So, but this one already is making this QQ plot, just this tail end is making me a little bit apprehensive. So not sure if left skewed would be the right way to describe it. We could, of course, let's quickly go do a histogram. I haven't actually included that. So let's do a histogram of these residuals and just see what happens if we look at them from that perspective. So, I mean, we have all of these tools. We can explore this, and it's good to explore it, but it's also good to then go and, yeah. So in this case, you are 100% correct. It does look left skewed. So, well, good instincts there. So if I look at this, if we didn't have this tail going off here on the left-hand side, if it maybe ended without these first two bars, then we could say, okay, maybe it would have been closer to normal, but there's something happening here on the left-hand side. So we saw something that bugged us. We looked at the data in a different way. We could, of course, have gone and done a box plot of this as well. Let's do that and see what the box plot looks like. So that question from earlier saying, do we have a, well, let's actually just make this horizontal. Is it a problem if we just look at one thing? This shows us we do need to look at it from a few different perspectives. So I'm going to do this, and we can see here, it does look, it's difficult to judge it from this, but you can see there appears to be some outliers on this side pulling it in that direction. So if I was doing this model like seriously, I would go look at those outliers and try and figure out what is happening there. It could be that that data was recorded incorrectly. It could be that this is a special case, that there's something happening with this data. So I think those are always the most interesting things. The things that don't fit with the rest is where we find the most interesting information. But yeah, you can go do a normality test as well, and see if that what that says. So I want to actually show you something else here as well before we carry on. So there are some diagnostic plots that I wanted to show you specifically that might make it easier to make all of these judgments. But first, I wanted to just show you, if we have this model, let's say, for instance, you wanted to predict a value, you can access your coefficients individually as well. So if you go and use this ALIM model that object that we saved it into, and you say coefficients, and we run that. You can see we get our intercept term and we get our slope parameter, or our slope estimate as well. But we can also individually access these. So if I went and said ALIM model, and I want the coefficients, I'll call coefficients, and let's just go back up here. I realized just now that flashing I'm seeing on my screen, you guys are hopefully not seeing. So hopefully it hasn't been disturbing you guys. But yeah, so if you look at this coefficients bit, you can see here, this is actually just a list with 2 values. So if I wanted to access the intercept, all I need to do is put the index 1 there, and there I have it. So same way, I could also go and look at, extract this coefficient, the slope one. So if I run that, I get that extracted, which means that if I wanted to do a prediction, let's say, for instance, I wanted to predict what would the head length be of a possum that has a skull width of, let's see what where those values were. I just want to see the approximate range. So let's actually just go and look at the skull widths, a summary of skull widths. Okay, so the minimum was 50 centimeters. So remember also, we don't want to go outside this range. It's dangerous territory to start predicting outside the range that you observe. So let's say we want to figure out what this would be if the skull width was 55 centimeters. I can just go and calculate it manually in this way. If I run this code, there I get my answer. So it does give me a title. It keeps the title of the first value that are referenced here, but we know it's not actually the intercept. This is a calculated value. There are ways of stripping it, but I can't remember right now how to do it. So it is possible though. Any questions so far about this? No questions, it seems. Okay, so then I wanted to show you the last bit, and you would probably think, but why did I go through all of this before plotting all these things manually? It was literally just to let us think first and then show what's available in R. So we could also just have said plot and inserted our model there, ALIM model. And if I run that, you'll see that it's going to give us our first plot. For some reason, I'm not seeing the plot yet. Let's just see if I run that. There we go. There's the first plot. So here it did the residuals against the fitted values. There was supposed to be another one. For some reason, it didn't display. I'm not sure why. I'll rerun it just now. But you can see that R actually does this plot for us. It points out some values that it thinks might be of interest to us. So it's basically suggesting maybe go look at observation 69, 17, and 98. Those could be influential outliers. And it kind of tries to show us if there's a pattern. So ideally what we would want is this red line should be very close to this line here, the 0 line here. And we can see here in the center it is, but then other things are happening. So it would be interesting to maybe go and eliminate those observations from our data set and replot or rerun all of this. And I'll leave that to you guys if you're interested to go play around with and seeing if that actually makes a difference to the fit of the model. If we press enter, it shows us the next one. It shows us our QQ plot. And it also points out these values here may be something that we need to go and have a look at. And we can again see that this is not 100% straight. And then there's another fancy plot that comes up, not this one yet, the next one, I think. But here we again can see here they have the standardized residuals and fitted values. And you can see there's a little bit of a pattern here. So this to me is suggesting maybe there's a relationship still in here that we haven't explained. So we might have to move over to multiple regression, include another variable in here to try and explain this variation, which we haven't explained yet. But yeah, you can see standardized residuals are automatically part of this output. And then this is the fancy one that I was talking about. So here you can look at things like Cook's difference, and things like that. So this has more, if I remember correctly, to do with outliers and trying to understand them. So again, these plots are done automatically, and you can see it does try and guide you. These plots try and guide you. So I just want to run this again, just to see, because there was a plot missing. For some reason, it did it last night. Today, it seems it doesn't want to do it. So I'm just going to quickly run through this and then clear everything and then see if it works. No, technology never wants to work when you want it to work. So let's clear that. And then I'm just going to run this for a final time and see if it works. Nope, that plot still doesn't want to display. So the plot that's not displaying is, I think, the first one we plotted with the residuals and not the residuals, the fitted values and the yeah, there's something going wrong here today. I think maybe because no, it's not that one. So the original plot that I created here with the observed values against the fitted values. So that typically displays, it displayed last night. I don't know why it's not displaying right now. So I think my computer's just gaslighting me a little bit. Any
Christine?
questions? Martin, yes.
No, there's a trick that you can use to view all your 6 plots without hitting enter and end. So you can you declare a variable called OP just above the plot L?
Yeah.
Where you are plotting, yeah.
So
Can
OP.
we have OP and then you assign?
Yeah.
Then there's a function called par, P-A-R.
Yeah.
And then inside you write MF row.
MF row. Yeah.
Yes, equal to.
Yeah.
And then you write a vector of what? 3 by 2. So it's C open bracket 3, 2.
Okay, let's do that. I've seen this before.
Enter.
And then we run.
Then after running the model, you are also supposed to say par in brackets OP.
Okay, so par in brackets OP.
After the plot, after plotting.
After the plot. Okay,
yeah.
Let's do that. There we go. Okay, so I've run that, and then I'm just going to zoom quickly.
I don't know why the P is 4. Are they not supposed to be 6?
Yeah, they're supposed to be more. I think my computer is trying to make us think we're losing our minds. But yeah, this is a very handy trick. I've seen it before in someone else's code, and I was wondering what that did, but I haven't played around with it yet. So this is very useful. I think it's very nice for output if you want to display your results properly. Thank you so much.
Yeah, if you want to remove that one, you can just run it dev off, so it removes
Okay.
every. Yeah, it just resets.
So that's
Yes, yeah.
perfect. Awesome. Thank you so much. Now we've all learned a new trick as well. Thank you. Any other comments or questions or suggestions or anything you guys want to share with us that you've maybe used? Yeah. So definitely, since it's only 4 items, then definitely we could make it 2. I think there's supposed to be another plot or another 2 plots in this output, and I'm not sure where they've gone because they were displaying last night, and then I restarted my R, and now for some reason they weren't displaying. There has to be a reason. Not sure what that reason is though. Cool. Any other questions or suggestions? I'm going to share my email address in the chat. You are welcome to email me if you have any questions or any comments or anything at all. I'm giving you my personal email address because you know you always reach me on that one. That's never going to change. So yeah, if there's anything that you guys are unsure about, feel free to send an email. And then I'll post this code on Moodle as well. And yeah, that's everything that I had prepared for today.
Hello, Chrissy.
Yes.
Is the C capital or small letter?
Sorry? It's small letter. Yeah, it doesn't really make a difference. It's supposed to be a small letter. I see it got capitalized, but yeah, it will work either way.
Okay.
Good.
I think that is different. That's the reason why I asked.
Okay.
Hi, Christine.
Yes.
Can you comment about any opportunities, especially postgraduate studies opportunities at the UP, studying statistics?
There's a lot of opportunities. I know that we have an e-science program that we're running in conjunction with Wits University. All of the details can be found on our department's website. So if you go to the UP website and you just go look for the Department of Statistics, there is a full brochure available on our website that goes into the details of all the postgraduate offerings that we have. There's definitely there's a lot going on. So for honors students, we have an internship program as well, where students they work kind of as tutors, but they also get some industry experience. They can do consultation projects as well. So they specifically, the consultation service that I mentioned earlier, they do consult and they learn on those consultation projects. So they get involved and get actual experience that way. Yeah, we have a master's program, we have a PhD program, very busy, very it changes all the time. So statistics is developing all the time. So there's so many opportunities. Like I said, with my research, I'm working specifically in spatial statistics. So we're looking at point pattern data. That's very applicable also if you're looking at image processing. But I wasn't using it in an image processing from that perspective. I'm specifically working at the moment with data from northern Tanzania. We were looking at rabies vaccinations in rural villages. So that's quite fun to work on. But yeah, there's so many different components to statistics and so many opportunities if you're interested in that. So yeah, lots of opportunities, but yeah, all of them listed on our website. So I'll just share the university website. So I can't remember the department, but I will actually put a QR code to our department's website on the Moodle platform. So then anyone who wants to go have a look at it can go and look at that QR code and scan it, and yeah, that will take them straight to our department's website. Any other questions or comments?
Christina, I don't see raised hands or
Nope.
further comments in the chat at the moment, or up in the air.
Yeah.
So I
Yeah,
think
no,
we shared with everyone your details, and I'm sure if there is one more message. Okay, no, there are a lot of thank yous. There are a lot of thank yous in the chat, so that's what's coming in fast at the moment. Yeah. So Christina, then on behalf of all the participants and of NITheP and the CHPC and myself, yeah, thank you so much for your time. We really appreciate, we are well aware that, you're busy with other lecturing duties, among other things. And we really appreciate the fact that you took time out of your busy schedule to be with us this month. So no, thank you very much. And you saw from the very positive response and the interest that you really hit the nerve of people and raise their interest for statistic and R, yeah, which was a tough call because they were primed to use Python for 2 weeks before they met you. So that, but I think that's very important, that people are exposed also to other environments. Once you learn one, it's not too difficult to adapt to another one. Yeah.
Absolutely,
so
absolutely.
That was really very nice. I also enjoyed refreshing my R skills because I didn't use it for about 20 years probably, or 15.
Well, to be honest, I was refreshing my own R skills, just preparing for this, because some of this is stuff that I don't use very often. So it was very interesting to me as well.
No, that's perfect. Yeah, that's perfect. Yeah, excellent. No, thank you very much, Christina. Thank you very much, everyone. And please don't forget to join us for the last session. We will start at 2, and I think the last speaker will be Emmanuel Dufour, who will bring his machine learning course to an ordered end. And straight away after the last lecture, we will have a little closing ceremony where we will mention the prize winners. So if you think that you're a potential prize winner, you should definitely attend the closing, the short closing ceremony after the last lecture. So approximately around 3:30, but I'm sure you will all be in the lecture of Emmanuel Dufour at 2. Yeah. So, Christina, thank you very much again. I really hope that we will stay in touch, because we'll probably organize similar courses again in future. So we will come back to you.
No problem at all.
Once you do something well, people keep coming.
True.
So thank you very much for that. We really appreciate it. And I hope that you might be able to join us this afternoon for the closing ceremony. Yeah,
definitely.
Thank you very much. Thank you very much,
Thank
everyone.
You.
Thank you, all of you, and I will see you again at 2. Yeah, thank you. All the best. Thank you very much, Christina. That was really nice. Thank you.
Thank you. Bye-bye.
Bye.